So to solve this LPP, solve graphically, so how many constraints are there? We have three constraints. As I said you, this is called the objective function. These three together are called the subjective constraints. This is called the non-negative restriction. So to solve graphically, there should be only two variables. So what are the two decision variables here? x1 comma x2. So the difference between the previous problems and this is nothing but here all the constraints are of greater than or equal to type. I said you the constraints all may be less than or equal to type, all may be greater than type, or a combination of these two. In the previous one we have the case where all are of less than or equal to type. Here we have three constraints and the first constraint is of greater than or equal to type and the second constraint is also of greater than or equal to type and also the third one. So whatever may be either less than or greater than or equal to type, first you find out the ordered pairs by considering each constraint as an equation. So this is an equation. If you put x1 is equal to 0, you will get x2 is equal to 1. If you put 0 here, 2x2 is equal to 1, which implies x2 is equal to 1. So if you put x2 is equal to 0, you will get x1 is equal to 2. So by putting one of the variable is 2, as 0, you can find out the other one. What is the ordered pair here? The first ordered pair is nothing but 2 comma 1. Similarly, consider the second constraint also as an equation. If you put x1 is equal to 0 here, this term will be 0, you will get x2 is equal to 3. Similarly, if you put x2 is equal to 0, you will get 3. If you put x2 is equal to 0, you will get 3x1 is equal to 3, which implies x1 is equal to 1. What is the ordered pair here? In the second case, the ordered pair is nothing but 1 comma 3. If you put x1 is equal to 0, you got x2 is equal to 3. If you put x1 is equal x2 is equal to 0, you got x1 is equal to 3. This is the ordered pair here. The third constraint is 3x1 plus 2x2 is equal to 6. If you put x1 is equal to 0, you will get 3x2 is equal to 6, where x2 will be 2. If you put x2 is equal to 0, you will get 4x1 is equal to 6, which implies x1 is equal to 6 by 4, which is nothing but 3 by 2. The ordered pair here is nothing but 3 by 2 comma 2. 3 by 2 comma 2. So the first ordered pair is 2 comma 1. The second ordered pair is nothing but 3 comma 1. Second one is nothing but 1.5 comma 2. So let us represent this on a graph to identify the feasible region. What is the feasible region? A feasible region is a region which is satisfied by all the constraints. So all the constraints should satisfy the region in which there is a chance you may get the solution for the given LPP. So it is a bivariate axis with one of the variable x1 on x-axis and other variable x2 on y-axis. So you can take the scale 1, 2, 3, 4, 5, 6. Here also the same 1, 2, 3, 4, 5, 6. What is the scale you have considered? On x-axis 1 centimeter is equal to 1 unit. And on y-axis also the same scale. So what is the first constraint you have? Here x1 is 2, x2 is 1. So this is the constraint for the first line, first one. What is the nature of this constraint here? It is of less than or equal to type. As I said you that if the constraint is of less than or equal to type, shade the area towards origin. If it is greater than or equal to type, shade the area above the origin. So what is the nature of the constraint here? It is of greater than or equal to type. So you can consider the region here. This is the region satisfied by the first constraint. So above the origin. What is the second constraint you have? 1 comma 3 means this is the point 1 on x1, 3 on y2. So this is the second one. This is also greater than or equal to type. The area is, you need to consider, is nothing but above the origin, which is nothing but this is the area you should consider. And what is the third one? Third one is nothing but 1.5 comma 2. Here this is 1.5 and this is 2. If you observe, all the constraints are of greater than or equal to type. So you need to consider the area for all these above the origin. So this is the area you should consider. So the one which is satisfied, or satisfied, the area which is satisfied by all the constraints is nothing but, from here it starts, this is the region which is satisfied by all the constraints. Here there is not a closed one, it is an we can call this is also an unbounded solution. In the previous problems we have observed, this is the for some cases you may find when both are less than or equal to type, you have a common region which is bounded, which is closed. In such cases we call the solution as a bounded one. Here if you observe, we have a common region but it is not a closed one, so we call, here we can write this as A, B, C, D. A, B, C, D is the feasible region. Feasible region. Moreover, it is unbounded. This is not bounded by any other line, so we can call this feasible region is unbounded solution. Let us read all the points here. What is A corner point here? A is nothing but 2, 0. What is B here? B here is nothing but 1.2. Here approximately you will get 1.2, 4, 0.4. What is C here? If you read here, C is nothing but approximately I am reading 0.6, 1. Better you do on a graph sheet, you can read the points easily. 3 is nothing but, means here also when all the constraints are greater than or equal to type, there is a chance that you will get an unbounded solution. Unbounded solution is nothing but a region, the feasible region is identified but it is an unbounded one. Likewise the previous one, you need to calculate Z the objective function at O, Z the objective function at B, Z the objective function at C, Z at D. What is the objective function given here? The objective function is 4x1 plus 2x2. So you substitute the first one, 4 into what is x1 here? 2 plus 2 into 0, which is nothing but 8. Second one, 4 into 1.2 plus 2 into 0.4, which is nothing but 5.6. Here 4 into 0.6 plus 2 into 1.2, which is nothing but 4.8. Here it is 4 into 3, which is nothing but 12, as this is 0, 3 into 2 into 0 will be 0. So what is the nature of the objective function here? Min Z, means among all these 4 points, you should choose such a point which is minimum here. What is the minimum point here? The minimum value Z is at the point C is equal to at the point C. Therefore, the solution is x1 is equal to 0.6 and x2 is equal to 1.2 with minimized Z, not max Z here. Min Z is equal to 4.8. So, first you should check whether all the constraints are less than or greater than. When all are greater than or equal to type, shade the area above the origin. Then try to identify the region which is common to all the 4 constraints and read the feasible region. Read the points at the corner points and find out Z at each of these corner points. Say Z at first corner point, second corner point of this feasible region. After that, check the nature of the objective function. If it is of minimization type, choose the minimum value. If it is of maximization type, choose the maximum value from the available corner points. That gives the solution of the given LPP. Thank you.